Good evening. So what we're going to focus on today is what happens with vectors that are at right angles. And we're going to be using eventually these vectors at right angles as the components that we're going to be working with in our vector resolution. And so we have to make sure that we lay the vectors tail to tip, from the tail of the first to the tip of the last. That's something that we really didn't have to do in one-dimensional vectors. It's essential in 2 dimensions. The resultant, or sum of a number of vectors, is then sketched from the tail of the first to the tip of the last. So that's going to be a very important process, tail to tip placement. Say that you're adding together 2 vectors at right angles. Vector A points north and vector B points east. You can use the Pythagorean theorem to find the magnitude of the resultant after you've placed the vectors tail to tip. And so for a vector north A of 8 newtons, adding to a vector to the east B at 6 newtons, we're going to have the Pythagorean theorem in use to get the resultant of 10 newtons as A 8 squared plus B 6 squared comes out to be 100, and the square root of 100 is the vector resultant magnitude of 10. Now we're going to also have to take care of the angle of the vector. When we are looking at vectors at right angles, just as we said, we're going to use the Pythagorean theorem, but we also want to use a trig function to determine the angle. The trig functions for vectors are just the sine, cosine, and tangent. So I just wanted to make sure we understand that our definitions of sine, cosine, and tangent have to do with their relationship to the angle in question. In this particular triangle, and we're always looking inside the triangle, the angle that we're discussing is 60 degrees. We see that 60 degrees has 2 rays that are making it up. One is the hypotenuse, and the other is side BX. So side BX is the leg of the right triangle that is helping to build the angle 60 degrees. So it is the adjacent side. And then focusing on 60 degrees again, vector BY is going to be the opposite side, the opposite leg, because it has no part of itself that is making up the angle. Here, the hypotenuse and BX make up the angle. BX is the adjacent leg. B, of course, is the hypotenuse, and BY is the opposite leg. So as you are working with these, you'll be able to use all sorts of different manipulations around the axis to get certain angles, as for example this external angle 120 degrees would be one that would allow us to say that the interior angle is 60 degrees. But we are also going to be very, very much focused on using the trig functions sine, cosine, and tangent correctly for right triangles. Keep in mind that the trig functions can only be used for right triangles, just as the Pythagorean theorem can only be used for right triangles as well.
Hola, and here's Mr. Black coming in. We have a 60 Newton vector, a force that's exerted north. We have another one, it's 84 newtons, that's east. Now we know that north is now 90 degrees and east is 0, so we know these 2 vectors are at a 90-degree angle. So first, we want to add one vector to the second through tail to tip. Oh, I screwed up. I have T instead of 2. Well, I'm not re-recording. So Remember how to do that? We want to take the vector here. I know that according to the scale is 6 centimeters. I slide it over and I redraw it so its tail begins at the tip of the 84 Newton vector, tail to tip. And so I want to be very careful. I draw it exactly the same, although we're not doing graphics, so we can get sloppy here. This is all going to be math. And there we go. I have my second vector, the 60 Newton, added to my first vector, the 84 Newtons. I've done a tail to tip, and so now I am ready to figure out what is my resultant vector. To draw my resultant vector, I draw it from the tail of that first vector to the tip of the last vector. Now this is only 2, but you could have 3 or 5 or 17 vectors. It doesn't matter. Wherever the last one ends that you've added, that's where the resultant vector goes to. So this is easy though. It's only 2. Drew it in. Look at that. Looks nice. All right. Beauty. And so that is my resultant, but I want to figure out, hey, what is the magnitude of that? I hope you notice we have an awesome right triangle. And as such, I can use the Pythagorean theorem. Pythagoras comes to the rescue. You guys remember what that is, don't you? That's the relationship between the hypotenuse and the sides. The hypotenuse squared equals side 1 squared plus side b squared. Well, side 1's 84 newtons squared, so that'd be a pretty big number, 7,056 newtons squared. Side b is 60, that's 3,600. So r squared equals 10,656. Find the square root. And sig figs, we are to 100 newtons. Yes, I have my magnitude, but I don't have my direction. That's where the trick comes in. If I could just find angle theta, since that is counterclockwise from east, in this case, that's going to be my direction, but I can't do it. Yes, you can. Tangent, opposite over adjacent. I know in this case the adjacent side is 84 and the opposite was 60, so I take my opposite, which is 60, divided by my adjacent, which is 84. And that number is the tangent of theta. But I don't really care about the tangent of theta. I want theta. I want theta. So what we have to do is find the inverse tangent of 0.71429, and that is how we'll get our angle. If you are rusty on the calculator, in your calculator you simply hit the second button, then hit tan for tangent, then go ahead and start a parentheses, and you would then take 60 divided by 84, because that's my opposite, divided by my adjacent. Then end parentheses, hit enter, and bang, you've got your angle. Now I can simply show my resultant, its magnitude of 100 newtons, its direction of 36 degrees, and that's how you do it.
Here's an example of vectors at right angles. This boat across a river is a very common vector analysis. So let's take a look. Diane rows a boat at 8 meters per second directly across a river that flows at 6 meters per second. What is the resultant velocity of the boat? So let's take a moment and solve this one. The first part, part A, is asking us what is the resultant velocity. And we tend to want to jump right to the Pythagorean theorem, which is perfect, except that we also have to include the angular measure. For boats on a river, you always want to make the angle with the shore. So you're basically going along the shore because that's where someone is going to be observing you and measuring the angle of your approach. So although the boat is headed directly across shore at 8 meters per second, we are going to add vectorially the 8 meters per second and 6 meters per second as legs of a right triangle. 8 squared plus 6 squared is 100, and so the square root of 100 is the length on the hypotenuse, and that is 10 meters per second as the resultant velocity. So we now are interested in finishing the description of the resultant by finding the angle that is made with the shore. To do that, we're going to recognize that the angle theta has as its adjacent leg the current, and as its opposite leg length the boat. And so what we can do is use the tangent function. And we can say that the tangent of the opposite side, 8, over the adjacent side, 6, is going to be equal to our value of degrees. And so if we do inverse tangent, parentheses, 8 over 6, we're going to get an angle of 53 degrees. We keep our calculator in degrees all the time whenever we're doing such a calculation. So there I have fully given the velocity of the boat as it's crossing the river. The resultant velocity of the boat along with the current is 10 meters per second at 53 degrees from the shore.